Good evening. This is a special session for the December round silver contest. Many students have taken the contest and felt scared. The questions were harder than the previous seasons. That is actually consistent to our expectation and the prediction. One particular feature that you might have noticed that is different from before. If your code pretty much, if you can solve the cases, say for example, besides the first case, which is given in the problem description, everybody will get it, right? So either you get the rest. So suppose we have total 10, either you get the majority of the rest 9 or you don't. That's the old style. So if you see the trick, you pretty much should solve all the cases. But if you don't see the trick, it will be hard. You may get 2 or 3 cases. It will be very hard to achieve, say, 75% for each question. All right. Now you have seen the scoring, right? Maybe subtask 1, subtask 1, you're going to get maybe 20% of the total test cases. Subtask 2, you may get 30%. Subtask 3, you get maybe 30 or 40%. Or sometimes the percentages, right? Percentiles may be different. But anyway, it's no longer the case. You get either most of them or you don't get them. Now it's, if you improve your code, you gradually, you may get, maybe 20% and then 30% or more, or maybe 20% or more. So this actually gives you the hope. Maybe you don't get the perfect score for a question, but you may still get the majority of the credits. So on average, if you can get 75% or more for each question, then you should be able to pass it. Actually, for the December round, the passing score is actually not 750 as normal, it is 700. So the passing threshold is lower, normally means the questions are harder than average. Actually, for this round, bronze, that's 700, silver, that's 700, and then the gold, that's normal 750. Okay, so if you have taken the December round silver contest and it did not pass, please do not feel upset. Actually, many students have similar feeling or experience. One thing I want to point out, if your code got stuck there and you could not figure out what went wrong with your code, you could only pass maybe say 5 out of 10 or 13 out of the 20 cases. Don't worry. Don't spend say more than 2 hours. Sometimes, right, I heard you might spend 3 hours on one question. That's not the right way to allocate the time. So give yourself about 1 hour, 1.5 hours on one question. If you still get stuck, move on to the next next question. Okay, 4 hours. That were a long time, but during the test, right? We all know time flies. Before you realize, okay, we won't have say 30 minutes left, and then you get kind of panic. Okay, please pace yourself. Get used to the speed. So how do you practice this one during the training? If you know a question that kind of challenge, right? You have not worked on it before. So give yourself about 1.5 hours. If you cannot solve it, then you need to change the viewpoint. You don't have to look at the answer. If the answer is available, right? Just change the viewpoint. Don't get stuck on that one. Then you know the pace that you need to take during the real contest. Okay, today we're going to go through maybe just one question in the December round for those who who were in my fourth semester in 2021, actually all three questions, probably you had trouble to solve them because we're going to go through the techniques in the list here, right? In the first half, we basically prepared for the foundation. And then start from unit 13 here, binary search, prefix, suffix. Some of you have noticed, right? We're going to do this a lot, actually. The float field, one question particularly would be fall into this one here, float field, find out the components. And then there are two techniques here for the graph traversal, BFS and DFS we're going to do. And unit 18, that's specifically for double indexing. Actually, one question, the first question, we're going to do this double indexing. Actually, this technique would be applicable not just to this question, actually would apply to two of the silver questions and also all three questions at the bronze level. So it could be a very important skill, but actually it's not that fancy. It's not that complicated. So actually today we're going to explain this idea using the first problem. Okay, this is the plan that we have now. It's up to adjustment. We might change the schedule depending on how the pace goes. If we're going to, we feel the need to add a session to analyze the question that we have seen, then we might change the schedule. Actually, we're going to start the spring semester on Feb, the weekend, the 5th and then the 6th here. That's the schedule. The Feb 5 and Feb 6th here, and then the first session would be analyze the questions we're going to see in the January. And after that one, we're going to have the normal 12 sessions. So this year, the spring semester, actually, we're going to have 13 sessions. Even though the first session, we're going to just have one period for each level. So we may have two silver sessions, but we're going to have just the Saturday and the Sunday, but we're going to have just one period for the weekend, Feb the 5th and Feb the 6th. And then after that one, we're going to have the typical 12 weeks for the spring semester. All right, okay, so let's go ahead and go through maybe the first question. I think I planned to have all three questions explained in 1 hour, but from the previous session for the bronze class, turned out we could not finish the three questions. Actually, we only did one question. So here I'm going to change the schedule, the plan. Also try to finish the first question. And then the other two questions, I'm going to put them into the videos. The videos for the two questions and also the first question will be available at the Google Drive, and you would get the announcement. So we're going to have the video files available as we did before, right, at the Zoom cloud storage. And we're going to send you the links so you can watch the videos. Okay, so let's go to the first question. Closest cow wins. Okay, refresh your memory. We have the patches here, K of them. K could go up to 200,000. Each patch, the graph patch, has two numbers. One is the position PI, the other one is the taste value, TI. P and T, the numbers could go in the range from 0 to 1 billion. And then we do have another set of the numbers to read from the input. That's farmer Noger's M cows. Again, M could go up to 20,000, and then the positions also would be from 0 to 1 billion. Notice here, the patches and then the M cows, they would all have distinct locations. So we would have K plus M different locations. K of them would be for the grass patches. M of them would be Noger's cows. Now we do have another set of the numbers N, that's for Farmer John's cows. We don't know the positions. Actually, we need to find out the optimal positions for these n cows so that Farmer John can claim the biggest taste value, the sum, can claim the biggest sum of the taste values. The criterion for the taste value would be if the patch, the grass patch here, if it's closer to Farmer John, I'm going to use A here, and then Farmer Noja B. If it is closer to Farmer John's cows, then Farmer John can claim the taste value. If it is closer to Farmer Noj or B, then Farmer Noja will claim the taste value. If there is a tie, Noja still has the advantage. So for a patch to be claimed for Farmer John, the distance D1 here has to be less than the distance D2. D1 is the distance from the patch to any of Farmer John's cows. So this would be the shortest distance of the patch to any of the n cows of Farmer John. D2 would be the shortest distance of this patch to any of the m cows of Farmer Noj. All right, so here, the brute force method does not work. It's just too big, right? K could go up to 200,000, M also the same range, N also the same range. So any one of them is too big to make it the squared. So if you do K squared, that's too big, M squared too big, N squared too big, or if you do the product of a K times, the product of any of the two of the three would make it too big. So we're going to do the analysis, the complexity, right? Can only do the n log n. Here, n would be the biggest of the k, m, and n. So in general, we're going to use n here. So referring to the max of k, m, and n. So we can only do this number times the log of this number. Okay, make sure this is clear. That's right. Okay, so we're going to, you're right, it's kind of have the priority for the patches and have the priority of the locations, the positions, right? And then how do you prioritize? Yeah, so this actually is a very smart question. Who wrote the question? Brian wrote the question. So it's not the same as, you have an array, you want to sort them, or you have a priority queue, you're going to, every time you have the element with the highest priority. It's not exactly like this one. You have to think about it. So eventually you're going to convert or reduce the question into a question that actually will check the priority or check how they have been sorted. That's a good idea. So Zhang He's idea is actually correct. Okay, so I'm going to go through the question and then try to analyze the question and then guide gradually to a solution. Here, we're talking about a working solution, means it is correct, and also it should be efficient enough so that we're going to finish the calculation within the time limit. Actually, for this one, this one did not have the subtasks. So either you see it, the trick, or you don't see it. So anyway, right? So here, if you do big O n complexity, then for sure it's not going to work. So you have to try for the n log n. So log n here, right? We're going to have the structures as we have seen in the fourth semester. The right. So some of the structures that we have seen, actually now this one here, would give us the log n part. For example, right, the sets, the maps. Sometimes the trees will give us the log n. Priority queue, which also would give us the log n performance. So we'll have some of the techniques. But here today, we're going to see particularly a technique we're going to use the binary search. Binary search is a technique that we're going to go through in unit 13, actually, the first unit in the spring semester. Okay, so now we're going to visualize. So that's the number 9, where all the patches and then the mcounts would be here. So suppose we do have the patches here. So the asterisk would be the patches, the grass, and we're going to have the farmer nodes cows. So I'm going to do have the farmer node. We're going to have okay, triangle here. Suppose these are the 2 adjacent cows from farmer node, and then these are the patches in this interval. So suppose this one is bj here. This is b at j plus 1. Okay, I'm going to use the b referring to farmer node. The second farmer John, we're going to use a. Okay, so notice one thing here. For this interval of the patches, grass patches, if we can allocate 2 cows from farmer John. So suppose this one is say I here, and I'm going to do another I plus 1. I could allocate 2 cows from now farmer John, so that I want to get the biggest sum of the taste values. Should be easy to see, right? If I put 1 cow from farmer John, right, on the leftmost patch, and then put another cow at the rightmost patch in this interval, then it's guaranteed. Right, exactly. So now we can guarantee all the patches should be counted toward farmer John. Right, because it's right, you can see pretty easily, right? For any patch, the distance to either AI should be closer to BI. The distance to B to A at I minus I plus 1 here, right, should be closer to B J plus 1. Then for each patch, take the smaller of these 2 should be the smaller distance of the 2, right, should be less than the distance of these 2. So for each patch, the distance, as we said, right, D1, the distance to farmer John's cows is less than the shortest distance from the patch to farmer Noge's cows. So if the condition is satisfied, then we know every patch, the taste value should count toward farmer John. So that is the case when we can allocate 2 cows for this interval. There is one special, there's one exception, that is if this cow is the last one from farmer node, say this is b at m minus 1. If this is b m minus 1, we're going to use 0 based. So cow b0, b1, all the way through b at m minus 1. And if we do have the patches after this one, then I don't need 2 cows to claim all the patches here. I just need 1. I'll just put the cow here. Then it's guaranteed, right? All the patches beyond bm minus 1 here, right, would have closer short distance to farmer John rather than to farmer node. So here, that's the exception. The last interval of the patches, I need just 1 cow, and then the same thing for B0. I also just need 1 cow. Just put it here, and then we would be able to claim all the patches toward farmer John.
Also, you can replace empty ones with grass patches that have a tastiness value of 0.
You're right, that's fine. If there is no patch between 2 adjacent cows from farmer node, right, then you don't need to allocate any cow there. Yeah, that should be fine. It does not cause any trouble for us. Good, okay. Now the question goes to, what if we don't have enough cows for every interval in the middle, right? We cannot allocate 2 cows in the middle for such an interval here. If you have no cows available, then for sure, right, just forget about it. But if you have the option, right, I can get one cow for this interval, then where do I put the cow? So that we can still claim the maximum sum of the test values in this interval.
I think that would depend on the individual taste values of the patches.
That is true. That is actually the key to the question. Actually, for I think many of you, right, have observed, yeah, I can do this one. I can see this. That's easy to realize. Now, if you have just one cow, where do I get it? And where do I put the cow? So the first reaction is, I should put the cow, Farmer John's cow, right? If there was only one cow available to do it, right? I should put it in the middle. Actually, put this cow in the middle does not guarantee you would get the best, I mean, the maximum sum. Okay, so let's have one simple example here. Let me still use the same example. So there is a cow here. There's a cow here for farmer B. And then the patches are like this. And if you select, you want to get the farmer A's cow here. If you only have one cow to put in this interval, do you want to put this cow here? Actually, it does not. In this case, actually, if you put cow here, right, actually, you cannot claim any patch in the interval because all these guys, right, would be closer to farmer B's cows. Okay, you say, well, can I try for any position? Then soon you're going to realize that's actually not a good idea. Why? You want to consider, right? Remember, right? The position goes from 0 to a billion. You don't want to try each integer value. Actually, the position for each cow could take the integer positions, can also take the half integer positions. So there go millions, I mean, billions of the choices. You don't want to go through there. But we do know one thing. Suppose I have the position, say, this is position P for the one cow for farmer A. I want to find out which patches in this interval farmer A can claim. Okay, so easy to see. Position BJ, I'm going to use the BJ for the location and then P for also the location. So all the patches to the left side of this bisector would go to farmer B. All the patches to the right of this bisector would go for farmer A. Suppose I have the position P for farmer A's cow, right? In the middle, this position, the patch, right, would have equal distance to BJ and also to P, and then they would go to farmer B. Only this part, the open interval, the patches in this interval would count toward farmer A because the distance here should be closer to this one. The same argument, you're going to have another bisector here. This is between P and B, J plus 1. The same argument. If a patch is in this open interval, then should have shorter distance to farmer A than to farmer B. You're right. Good observation, everybody. Okay, so once you realize this one here, then life actually becomes easier. So no matter where I put this cow P, I mean, put the one cow from farmer A, right, at the position P here, right? No matter where I put it, as long as P is between BJ and B at J plus 1, then I would have the space controlled by this cow would be in this one here. Suppose this is the left-hand side, this is the right-hand side. So L is just P plus BJ over 2. The right-hand side of this interval, right, should be P plus B at J plus 1 and over 2. Or in other words, the length of this interval controlled by this one cow should be R minus L. P is canceled here, so should be just B at J plus 1 minus BJ all over 2.
Also know that's an exclusive interval, so it doesn't include the left side and the right side.
You're
Because
right.
of the fact that if they're the same distance, then no, she gets the pass.
You're right. Very good. Very good. So this is an open interval, right? Does not include the both ends. Okay. Does this help for us to solve the question? You don't know where to put this P, right? Still a lot of choices to put the P, but don't worry. Okay. So we're going to have okay, so we're going to have change the viewpoint. Don't think about this P. Think about it. If I have the first patch that is controlled by this cow, if I have the first patch, right? I want to say this is the first patch that will go count toward farmer A. Then I know the rightmost one. Suppose this is the left end boundary. This is the right end of the boundary. Then R should be less than L plus this. I'm going to say, right, this one here should be the LEM, should be LEN over 2. Actually, I'm going to put R to be this one here, and then the space, the interval, right, controlled by this cow should go from L to R here with open end at R. Okay, so change the viewpoint. Here we can easily analyze the territory controlled by this cow is from L to R. Both would be open-ended. But anyway, right, if you say this interval open-ended, right, you're going to always have the first patch. Then why don't I start from the first patch? As long as this R, it is no more than this one here, then I know the distance, right? I mean, the length of this interval is less than LEN over 2. Then I can just put the cow here, put the P here. All right, so hope this makes sense. So now we're going to have an idea. I'm going to change the location of this position P so that I could have a window of length LEN over 2 open. Length should be less than LEN over 2, not equal to, less than LEN over 2. I'm going to have a window, and this window is actually, we're going to have a special name. We're going to call this one the sliding window. What does it mean? We're going to actually move this window. Start from here and move it or slide it between this BJ and BJ plus 1. Every time the length should be fixed, is actually right less than LEN over 2. Okay, calculate, that's great. Okay, here a little bit different from math. In math, actually, the LEN could be any real number. So if you say this one is less than LEN, that's fine, right? It could go arbitrarily close. If this LEN is a 1, half of it, right, would be 0.5. So I don't have to get exactly 0.5. I could get 0.49 or 9999. As long as this one is not exactly 5, then this is fine. But here we know, right, BJ and B at J plus 1, they're all integers. Then you know you cannot get arbitrarily close to this one. Actually, the first patch, the last patch, both of them would be integer coordinates. So here you cannot have the ambiguity, right? If this one is the rightmost patch, then you cannot have another one because you're going to jump at least 1 unit, since all the patches have integer coordinates. So that should be easy. Okay, we're going to have another technique called a sliding window. Find out the maximum sum of the test values of this such window. And we're going to slide the window from this left end here, BJ, to the right end. Or to be more precise, right? This window, the left end should be bigger than this BJ. The right end of this window should be less than BJ plus 1. As we slide the window, we're going to keep track of the sum of all the patches in this window. Every time you're going to have this sum, slide the window from the left to the right, and then during the sliding process, we're going to keep the maximum record. After we have examined all such windows, we're going to have a record sum that could be achieved using just one cow to get the sum of the taste values in this interval bj through b at j plus 1. Well, to be honest, the questions here may be harder than Amy. Well, yeah, before in the seasons 2016, 2017, some of the questions you might think, well, they would be easier than the Amy. Well, it is actually comparable, right? If you say silver is comparable to Amy, and then gold would be JMO, and platinum would be comparable to AMO. You can do that, but now actually silver, I think many would agree, right? Actually, get the promotion actually is harder, right? It's harder than the Amy level, just because for many of you guys, the training for math started when you were much younger, but training for USACO, actually it's our philosophy or our belief, you should start after you have taken algebra. So most of you guys, right, started the training for USACO from middle school. The oldest one actually we would take actually from the 6th grade or 7th grade. And many of you actually started in high school, 9th grade, or even 10th grade, all right? So it's not surprising, actually, I have talked to many students this season, right, 2022, that's the first time, to the best of my knowledge, USMO has changed, moved the date, right, for MC 10, 12 to November. That is even before the USACO first round. I have never seen this before, and I'm pretty sure right, USMO has felt the pressure. Actually, I've been let me move all these guys, just give you the counts. Back here, the participants here, this number close to 10,000. You know, this number that was about the total for the 4 rounds, just maybe 3-4 seasons ago. Now just 1 round and just 1 bronze level, this number has been bigger than the total of the 4 rounds for all the levels. So here, we have seen the exponential growth for USACO participation from students and also from parents. So don't feel surprised. Actually, if you have a rough count, every year for Math Olympiad, the number of the students would be about 300,000 nationwide. And for USACO and USACO Physics Olympiad, about 5 years ago, maybe 6 years ago, the number annually would be about 5,000. Now, USACO probably still would be the same number, but USACO, right? Now, this one has been much, much bigger. Actually, now for the number of the people preparing for the contest, some of them, right, may started training, have not started taking the contest. The number actually, I would say close to 100,000 nationwide. So I would not be surprised in 5 years, the number of the participants for USACO would overtake that number for USMO. Why? Because it is, right, many of you have known this one. I've been saying this one for a long time, because the training for USACO actually would be useful for your college and also for your job after you graduate from college. Actually, we have a lot of requests from college students say, I need to prepare for an interview to Google and Amazon, for Microsoft, and so right. we need the training for USACO. Actually, the training for silver level, gold level would be perfect for your job interview after your college, graduate from college. Okay, go back to the question. Okay, sometimes I can see your comments, sometimes I may be too busy to see. So if you do want to raise your voice, right, just speak out. All right, so now let's go back to this one here. 2 cows, we can claim all the patches in the interval. 1 cow, we're going to slide the window to make sure we're going to get the maximum sum of the patches in this interval. Okay, so now you say, that's good. Suppose we can do both of these things. Actually, the first one, right, that's easy to do. This one may be a little bit harder, but still, we can do it. Suppose we have done it. Now what are we going to do? For each interval, I have the contribution from 2 cows or from contribution from 1 cow. Now I have n cows from farmer A, right, farmer John. How do I allocate the n cows so that the total sum would be as bigger as possible? Okay, so here we're going to, again, think about it in a slightly different way. As you say, you can get 2 cows, you can get 1 cow here. Okay, I think probably I'm going to try a one idea here, one approach. Hopefully this will make the life easier to solve the question. So suppose I have 2 cows. 2 cows can be allocated to this interval. Then clear, right? I'm going to get the full, every patch. Okay, that's good. Actually, we're going to use a technique called the prefix sum to find out this one. You don't want to use another layer of the loop to find out the sum of all the patches in this interval. We're going to do this one in a moment. You're going to see that is actually not too bad. And then the suppose I have 1 cow, right? Suppose I have 1 cow, the contribution would be the maximum of the sum, right, when I slide the window. And then the difference, so suppose I'm going to say this is S2 here, this is S1. 1 cow, S1, the maximum. S2, that means everything, every patch in the interval. Then you can think about it this way here. We're going to assume S1 is the contribution of cow 1. Cow 2, the contribution actually would be S2 minus S1. All right, so here, right, suppose I have 2 cows, there will be S1 plus S2 minus S1, that's still S2, the same. But now I'm going to split, right? If you can have 2 cows, then both the sum would be there. But if you have just 1 cow, I'm going to have S1 there. If this S2 is very big, right? S2 minus 1, S1 still would be pretty big, so should still have the priority to be chosen among the n cows from farmer John or from farmer A.
So I want to say something. So the 10 to the 9th here is for the tastiness values, not for the positions. The positions only go up to 2 times 10 to the 5th. The positions.
No. Positions still would go 10, 9.
The position wasn't positions specified to only go to 2 times 10 to the 5th?
No. This is the number of.
No, that was the number of grassy patches.
Yeah.
Oh.
These locations would go from 0 to 10, 9.
Oh, okay.
Good. Very good. Thank you. Okay, so now we're going to go through here. I'm not sure we can finish this. You know what? I'll just go through this implementation. Okay, some of the tricks may be a little bit hard to go through. I plan to write down the solution 9 after 9, 20 minutes, probably not enough. Okay, I'll just go this solution here. So K, that's number of the patches. M is the number of the cows from farmer node. N, that's number of the cows from farmer John, A and B. Patches, here we're going to have an array of size K rows, 2 columns, right? We have K patches, 2 columns. Because we're going to store the values. Location would be at column 0. Taste value would be at column 1. Actually, this is incorrect. Taste value. Okay, so why I want to use long, because later want to do the add them together. I don't want to do the casting. So it's okay, just make it by default, everything is long. So later when you do the sum, you don't have to cast from integer to long. Okay, so when you have an array of 2 dimension, you want to sort them. You want to sort the patches right from using the position from the leftmost to the rightmost one, increasing order of the positions. We have done this before. Oh, as I said, right, long, because later when I try to add the taste value in the interval, since each one could go from here, right, taste value could go from 0 to 1 billion. Each one is in the range of integer, but if you add them together, this may go out of the range of integers. So eventually you have to use a long to find out the sum of the taste value of the patches. So I'll just make them to be long. This one, actually, the space requirement is not too big. Why? K is at most 2 times 10 5 times 2, right? That's 2K of the integers, right? Each one takes 8 bytes. Each integer takes 4 bytes. Each long integer takes 8 bytes. So this would be 4 times 8, 32 times 10 5. So 3.2 times 10 6. That's bytes. What does this mean? This would be 3.2 megabytes. And what is the limit for the memory usage for each submission? We have up to 256 megabytes. So if you take the long integer, right, that's 1.6 megabytes. If you take long, that's 3.2 megabytes. None of them would threaten, give us threat, right, to the up limit 256 megabytes. Actually, we don't worry about this one. You're going to hear this one or experience. For USACO contests, the storage for the input numbers always is not an issue. That's why you always see the number, right? The N, K, M, right? Always will be in the range 10, 5. You never need to worry about when this number, right, it could go up to 10, 5, 10, 6, 10, 7. Why? Reading all the integers would take pretty much all the time. So you don't have the time to do actual calculation. So for USACO, for ICPC, all the contests, the input size always would be in the range 10, 5, 100,000 or 200,000, sometimes maybe even bigger, 400,000. But I've never seen any question you have to read, say, a million integers. So don't worry about this storage for the input integers. Okay, now we're going to sort the integers in this array patch, right? 2-dimensional array. And we have also seen this one in the 4th semester, sort an array. So we're going to use the number expression. P1, P2 are 2 patches in this array. Actually, P1, P2 actually are also 2 rows. Which row goes first, right? We're going to have this one here. If P1, 0, column 0, that's location. If it's less than or equal to P2, 0, right? The location of patch 1 is on the left side of patch 2, then we should say -1, because this number expression, when the value returns negative, then P1 goes first. Otherwise, P2 goes first. So that means we're going to sort the patches from the left to the right. All right, so okay, this part should be easy, right? Many of you have known this technique. So that's the number expression that will make your life very convenient. You don't have to write a comparator. You don't have to do the extension, implement the comparator. So this will make the coding very convenient. Okay, now we're going to have the prefix sum. This is another technique that we're going to go through here, right? Unit 14, the prefix sum, the suffix sum, the prefix maximum or minimum. Okay, here we'll just explain the idea. You're going to have, given an array here, suppose you have an array, say A, you're going to find out the value from A1, A2, all the way through, say, AK. So SK would be A1 plus A2 plus all the way through AK. So that's the partial sum, right? Many of you in a math training, you have done this one. Now, this array S, it goes also right as 1, S2, S3. So K goes from 1 to all the way through. So suppose this one is A and the last one goes through N. Now this prefix sum or the partial sum array can be used to find out the query. You want to find out from, say, position I to position J. That means you want to do AI all the way through AJ. This one, you don't have to write a loop. Why? Because this one is easy, right? This is A1 all the way through AJ here, minus A1, add all the way through AI minus 1 here. Right? If you cancel the part from A1 through AI minus 1, then you're left with I through J. So this part, right? The top, this one part, that's the SJ. This bottom one is Si minus 1. If you have saved this S array, then this partial sum would be can be achieved by just one operation rather than writing a loop. So that's what we're going to have the partial sum. So this is the partial sum or the prefix sum, the same thing. So with this PST, T for denote the taste value. Then later, if you want to get the, this is a BJ, that's the BJ plus 1, all the patches in the window, right? If you want to get the total, the sum, you don't have to write a loop. Just go from here to minus this one before, then you get the prefix, I mean the partial sum in the middle. Okay, there is a comment. PST, okay. Okay, thank you. Well, sometimes the variable name could be, you know, everyone has your own naming scheme. So sometimes maybe interesting to others. But PS is actually a common name. You may have, say, T and some other place. Anyway, oh, I've changed. A, that's for farmer Noja's cows. Okay, we're going to read the position of the N cows from farmer Noja. That's A. Again, I'm sorry. Actually, I did not use B for farmer John. Anyway, so now this one, if you want, right, I'm going to just switch this one here to make it B. Okay, for Eclipse or for IntelliJ, this is very convenient. If you want to rename the variable, right, actually it would, you can do this one very efficiently. Okay, read it, and then we're going to also sort the positions of the M cows from farmer B. Okay, now we're going to calculate the contributions of the farmer John's cows to the total sum. Okay, we're going to have a list. How many of them? Actually, I'm not so sure yet. But for every interval partitioned by farmer Noja's cows, farmer B, right, we're going to have either one contribution or two, because to the first block, so this is B1 here, right? This part I have just one contribution. This one BM also, that's just one contribution. And in the middle, you may have two, S1, one cow, or S2, two cows. Okay, so this one should be at most 2M plus 2. M is number of the cows from farmer B. They could cut this one into M plus 1 intervals. M plus 1 intervals, right? This one has 1, this one has 1 in the middle. M minus 1, each one of them is 2 plus 2, actually would be just 2M, not 2M plus 2. Okay, at most 2M of them. Okay, now we're going to say for each interval partitioned by the cows BJ and BJ plus 1, we're going to consider the contribution. Now, we're going to have the two indices, as I mentioned earlier, right? We're going to have the double indexing, which is a technique that we're going to use unit 18 in the spring semester we're going to cover. So X is the index for farmer B. No, actually for the patch. Y is the index for farmer B here. I've used here K, that's for the patch here. And M, that's for farmer B's cows. So notice, right, my convention, if you have X goes K, then X always goes with K. Y goes with M, then Y always compare with M. Okay, so now we're going to find out the pad, this interval from X to Z here, that between the two cows B, well, actually this should be B. Okay, I used y here rather than j, and I actually used y minus 1 through by here. So this is another technique that we're going to do a lot. Start from x here, z start from x. You don't want to go repeat the check-in before x. Okay, we're going to find out from x all the way through the next cow by here, all the patches between from x excluding z should be between by minus 1 and by. The reason is the criterion is easy. If z is less than k, right, z cannot go beyond k, and patch z, the location should be on the left of by, then we should always increase z by 1. When this loop is done, then z would be the first index of the patch that is to the right of by. If it's on the left of by, should always increase. And this one, be careful, right? Because all the patches have distinct locations of by. So this equality will never happen. Okay, notice, right? After this while loop I highlighted, the patches from x inclusive, and then through z exclusive would be between the two counts from formula b at y minus 1 and by. Now, if x is less than z, that means there are patches in this interval, right? X less than z, then I know I have at least one patch in this interval. I'm going to do this one. If this is not the case, then you don't have to do anything. There's no patch in this interval, then just ignore it. Okay, so now if y is 0, that means, right, we have the first patch here, the first cow from formula b. Actually, I start from index 0, not from not index 1. I mean, not 1 based, it's 0 based. So everything to the left of b0, I could have just one cow and claim all of them. So I'm going to do list will add the partial sum of all the patches from 0 through z minus 1. So here, right, you notice the first time I'm going to apply the partial sum trick. You add from the patches from 0 all the way through z minus 1. You don't have to run a loop, just find out this partial sum from 0 through z minus 1. Just one operation rather than a loop. Okay, that's the case when this y is 0. Now, if y is positive, then we do have the two, right, from by minus 1 and also by. Now we're going to consider the two cases when you have two cows or one cow. Two cows, if x is 0, because you cannot do x minus 1. If x is 0, then you just go from 0 to z minus 1, the same like this. If x is positive, as we said before, right, you're going to do this is z minus 1, the last index in this interval less than by, minus this should be x minus 1, because we have to include from x to z minus 1. So that's the partial sum between x through z minus 1. Again, that's another occurrence of the partial sum trick. Okay, now we're going to have the S1, that's the contribution of one cow, and this is the sliding window. When we slide the window, we're going to have the maximum value of S1. So the max contribution of one cow. If there is no cow, no patch, right, then value will be 0. If you have more than, I mean, if you have at least one patch, then this number should be positive. Anyway, we start from 0. If at any time the sliding window sum S1 is bigger than the record, we're going to update the record. Now, the length from by minus 1 through by is here. The length, as we said, right, we're going to say, if you put one cow there, the interval that this cow controls, right, would be length over 2, and actually would be open, cannot reach length over 2, should be less than length over 2. Okay, so now start from x here, right? Suppose the window controlled by this cow, the left end is x, to the right, I don't know, we're going to try this right. So we're going to have this inner loop here, right, starts from x here. If it is less than z, right, has to be less than z. Everything is from x less than z here. And also the patch right minus patch left should be less than len over 2. I don't want to do the division by 2 because what if len is odd number, right? So it's better to do times 2 less than len. If that's the case, that means this patch right still is controlled by the current window, right? If this distance is less than any len minus over 2 here, then the patch is in. Then we're going to add the contribution of this patch to S1. S1 is the sum of all the patches in the current window. And then we're going to increase right by 1 until this right is not in the current window, then we're going to stop. Now I'm going to say, right, S1M should be updated if S1 is bigger than S1M. This should be easy to understand. S1M is always the maximum record of the contribution of any one cow as we slide through the window. And then for the next iteration, right, we're going to say the left end will start from X, and the next will be X plus 1. The next time would be X plus 2. Every time we go slide the window to the right, this left should go out of the window. So we're going to say exclude the contribution, right? We're going to say minus the contribution of this patch left. Okay, make sure this makes sense, right? So even though there are 2 levels here, 2 layers of the loop, actually every patch will enter the window once and exit the window once. So this part, actually later when we go through the double indexing, we're going to analyze the complexity is actually linear rather than square. All right, so we're going to finish this. And then after we finish this, we have the contribution of 2 cows and also the maximum contribution of 1 cow. So we're going to say that's the contribution from the first cow, cow 1, and that's the contribution from the second cow if we can have a second cow in this interval from by minus 1 through by. Okay, after we have done this one here, right, don't repeat the processing for the patches, right, to the left of Z. X now should jump to Z here. X should jump to Z. Next time, we're going to process from Z to the right. So again, every patch is processed once, even though we have 3 layers here, the while loop here, the for loop here, the while loop here, right? Every patch is processed once. Every cow from farmer B is processed once. So the overall complexity for this loop from 935 all the way through 963, the complexity is actually linear. Okay, yeah. Actually, this is a good one, but we don't want to spend effort here. Anyway, your improvement, right, is actually not significant. As I said, right, if the total quote is 256 megabytes, if you can save 1.6 megabytes, actually does not make much sense, much difference. If this 1.6 megabytes, right, would cause either failure or pass success, right, then we're going to do that. If it does not matter, then we're not going to spend effort. You always know, right, in computer science, we always try to improve the bottleneck. You don't want to improve the part that is not important. Okay, so now after we finish this, actually we have done, right, for this interval, we have the contribution from 1 cow or 2 cows. Now, after we have done this one, we're going to, one more thing. We're going to have the last block. The last block to the right of, actually, this is BM minus 1. Again, this one, you're going to have just 1 cow that can claim all the patches to the right of BM minus 1. Now, we're going to sort the contributions in the list in decreasing order. So we're going to have this number expression one more time. Why I don't want to just A minus B or B minus A. That will give us a long integer. And then this one, by default, you're going to return an integer. So here, if A is big than B, big than or equal to B, then you say -1. So the value returned. If it's negative, then A goes first. Otherwise, B goes first. So this is to sort the contributions in the list in decreasing order. And this list, right, may have more than n numbers. That's okay. We're going to take just the first n. Take the first n contributions that corresponds to the n cows from Farmer John and add them together. That's the answer. Okay, you could actually store this one in integer, and then when you do the partial sum, you're going to make it long. And also the list, you also have to make it long, because when you do the partial sum, you may still go out of the range. Actually, right? If each number, the test value is at most 1 billion, 3 patches, if you add them together, that will go out of the range of integers. So here, I just want to make it easy, make it uniform. The location, that's integer. The patch also integer, right? To avoid the addition later, I mean the partial sum, right? To make it integer cast to long, just make it default long. That's okay. You can also implement another, implement a helper class where each patch, right, is an object. It contains 2 pieces of information. One is location, one is taste value. You can also sort by this, using the number expression the same way. Actually, I got a little bit confused, right? By this one, actually, we don't use binary search. I'm sorry. Binary search is used for connecting and also for the, no, just for the second question, connecting. Question 3 does not need binary search either. Anyway, the partial sum is used in question 1 and also in question 3. And so hope this one has been explained to your satisfaction. If this one is not clear, I hope you could go through the implementation one more time. So let me send you guys, everyone, right? Send everyone a version of the solution. So here, this would be silver. And question 1. Okay, and the other 2 questions, I don't have time to do it today, but I would be able to send you also the file connecting. Okay, that's fine. And also question 3, the convoluted intervals. Okay, each one of you, right, should have received the solutions. Actually, I sent you the Java version, and if you want to get the C++ version, I could also do that one. I can upload all the solutions to the Google Drive for the 4th semester from last year. If you have that one, you can go check there. And if you don't, we would upload the video files and also the source files into a Google Drive link later. We planned to have the 3 questions explained, but 1 hour is not enough. So we would upload 2 extra videos just for video, and then you should be able to watch them. And it is our plan to have another the review session that is actually on the Feb the 5th. The 2 silver sessions, we're going to share 1 2-hour period, explain the 3 questions. And then after that, the Feb 12th, start from there, we're going to have the 12 sessions for the spring semester. So please check the schedule. Actually, schedule has changed a little. The 4th semester, we had the silver version on Sunday, and then the other one on Tuesday evening. Now, the 2 silver versions now have both been on the weekend, one on Saturday and one on Saturday, one on Sunday. So please notice the time change. All right. Okay. If you have any other questions, please send me messages. Okay. Any other question about the admin, please send it to the info@momentum.org. you can check the website. I mean, check the email address at the website. All right. Okay. I'll stop here. I'll see you guys later. Thank you.